live on YouTube.
So good morning, everyone. It is a very, very wonderful Monday morning. Mondays are my favorite day of the week. So, to get started, for first thing, join table group in Discord. Otherwise, I will put you in a breakout room. And then I want you to start with the warm-up question. So in the Zoom chat, I want you to answer the following. In this lovely story, me, Mr. Who, so I'm sleeping in my bunk bed. When I accidentally roll off of the side and I start free falling to the ground. My bunk bed is 2 meters above the ground. So I want you to figure out how long it takes for me to hit the ground from the moment I roll off the bunk bed and how fast am I moving at this point. So let's take a few minutes to see if we can figure this out. How long does it take for me to roll off the bed and how fast am I moving at this particular point in time? So for those of you just joining us, so join a table group in Discord, otherwise I will put you in a breakout room. And in the Zoom chat, I want you to answer the following. In this scenario, the story, me, Mr. Who, sleeping in my bunk bed, when I accidentally roll off of the side and I start free falling to the ground. So my bunk bed is 2 meters above the ground, and so I want you to answer the following questions. How long does it take for me to hit the ground, and how fast am I moving at this point in time?
Yeah, I think it's like 9.8.
When you are ready, put your answers in the Zoom chat, and let's see what we can get.
Hi. Sorry. Hello. What? You tell me.
When you're ready, put your answer in the Zoom chat, and let's see what we can get. We got 2 answers so far. Charles and Austin. Jack. Let's get a few more answers in here. We got 3 answers so far. Can we get like 3 more? 3 more answers? Let's take another minute or 2, and then I will show you how I did. So here's I'm gonna show you how I did it. So first off, I think the best way to start is we first want to identify which equation I think we can start with. So the best equation to start with any sort of acceleration problem is the general displacement function. So what we're going to do is we're going to model the position of me with So for this one, because I'm falling vertically, instead of x of t, this time I'm going to use y of t. So y of t is equal to my initial displacement plus my initial velocity times time plus 1/2 times a t squared. Okay, so what I'm going to do here is I'm going to start subbing things in. So one of the key things here is we want to look at where I am at the very end. So y of t tells me my position with respect to time. And so what I want to figure out is when do I hit the ground? Or when is my y value here 0? So I'm going to, so what I'm going to do is I'm going to plug in 0 for here. So 0 is equal to, my initial displacement is I initially start off 2 meters above the ground. So I'm just going to put a 2 here for why not. Okay. So my initial displacement, my initial velocity here is 0 because I start falling. I haven't already been falling. So this is just going to turn into 0, and then 1/2 at squared. So this is going to be, because I'm free falling, this is going to be 1/2 times t squared. G is negative 9.8. So what I'm going to do here is this is going to turn into 2 minus 4.9 times t squared. So 0 is 2 minus 4.9 times t squared. What I'm going to do is I am going to drag the 4.9. So what I'm going to do is 4.9 t squared equal to 2 over 4.9 is equal to t squared. That means t squared should be roughly 0.4 roughly. So t is what, roughly 0.6 or so, give or take. And then to figure out my final velocity, what I'm going to do is I'm going to take my acceleration. So what I'm going to do is use this equation. Acceleration, the definition of acceleration is your change in velocity over your change in time. So my acceleration is g, so negative 9.8 is equal to my change in velocity over my change in time. My change in time is 0.6 seconds. So multiply both sides out, and I'll get my change in velocity is around 6 meters per second. I'm not gonna do the exact number here. I don't really know off the top of my head. And then, so because I initially start off at 0, this should be -6. Because I initially start off at 0, my velocity, my final velocity should be -6 meters per second. Did that sort of make sense to people? Yes,
Yeah.
no? Okay, we got one yes.
Will we do more problems like this?
Yeah, so we're gonna do some more today. We're gonna continue with the asteroid problem, which is gonna have a lot more acceleration to do as well. So yeah, we're gonna get a lot more practice with acceleration. So we're gonna do that today. Anyone else have any questions about how I did it? Okay, so what I'm going to do now is we're going to turn it into the asteroid mission again. So what we're going to do is we're going to look at, so I think last time, I think we finished, I know I went over question 2 as a class. Did I go over question 3 last time, how we did that? Okay, so, okay, so first off, did everyone get a chance to finish question 3 on the asteroid mission that we did last time? The part where we start looking at the missile? Yes, no?
I think we started looking at it.
Okay, so what I'll do is I'm going to give you some time to keep working on the asteroid mission. When everyone is done with question 3, I'll go over it as a class, and so that way we can all see we're all on the same page. So I'm going to let you get started, and then in a few minutes, I'll check and see where everyone is. So I'm gonna go over question 3 right now. Did everyone get a chance to finish question 3? Yes? No?
I did.
Okay. Okay, so what I'm gonna do here is I'm going to. So what we're gonna do is we're gonna first write down a function for the missile's position. So the missile's function is yt is y naught plus b sub naught times t plus 1/2 at squared. So the initial position is 0 because it's fired from the ground. Its initial velocity is 4. And then we're ignoring gravity for this missile because I said to. So it's going to be 1/2 times 11, I think. So it's plus 5.5 t squared. And that's y of t. So to figure out where the missile hits the asteroid, what we're going to do is we are going to. Oh no, the missile is accelerating at 6. I don't know why I said 11. I think it's 11 in different column. It's plus 3t squared. Yeah, sorry. 1/2 times 6 is 3. So what I do next is we're going to figure out when the missile is hitting the asteroid. So missile is hitting the asteroid. So to do this, what we're going to do is we're going to sit down and set the missile's function equal to the asteroid's function. So 4 times t plus 3t squared. So the asteroid is initially starting from a position of 10,000. The asteroid is moving at an initial velocity of -17 times time. And then the asteroid is free falling, so it's moving at, it's accelerating at this. This is just 1/2 times 9.8, which is 4.9. So some algebra here. 0 is 10,000 minus 21 times t minus 3t, 7.9 t squared. And so t is, I think, 34 seconds, I think. Is that what people got? 34 seconds? About, give or take. And the height of this is y of t, 4 times 34 plus 3 times 34 squared. I don't know off the top of my head. Let me do it real quick. Unless someone else already has an answer for it. Let me do it real quick. 4 times 3. Okay, I got 3,604. Weird position. Okay, so what we're going to do next is we're going to draw a acceleration, position, and velocity versus time graph for the missile. Oh, yeah, we're first determine the final velocity, sorry, and then we're going to draw a graph. So the final velocity of missile is, so let's first write off a velocity versus time function for the missile. So the velocity of the missile, t is the v naught. So v naught is the initial velocity of the missile, which is 4. Plus acceleration, which is 6 times t. So t was 34 seconds. We're just going to plug 34 into here. And this should be 4 times 6 is 60 times 3, which is 204, I think. And 204 plus 4, I think 208 meters per second. I think I might have done it a little, it should be something like this. And then last but not least, to draw the graphs for the missile. So the position versus time graph for the missile. So let's start with the acceleration versus time. The acceleration versus time is just going to be a constant positive 6. Velocity versus time is going to be starting off at 4. That's going to, because it's accelerating and getting faster, it's going to be a positive slope. And the slope is just going to be 6. And then for the position versus time, it's going to start off at 0, and it's going to just be curving upwards because it's accelerating, getting faster. Does that make sense for question 3? Okay, cool. If you don't have questions, I'll just keep working, and then we'll see if you can go over question 4 before class. So I'm gonna go with question 4 now, just so people can see how I do it. For question 4, what we're gonna do is we're gonna first write down a function for the missile. So this is for question 4, the one with the missile that's going straight up and it's coming back down. So what we're gonna do is we're gonna write a position function for the missile. So yt is the initial position, which is 0, plus its initial velocity, which is 68.6. It's going upward, so this is positive. And it's in free fall, which means that the only acceleration to it due to gravity is gravity. So it's minus 4.9 squared. So the next question I believe is asking you how high up does the missile go before it starts coming down? So what I am going to do is I am going to show you that this can be done in 2 ways. So I think this can be done in 2 ways, I believe. The one where it's, I'll just show you how I would usually do this. Okay, so first off, what you would do is you would so let's draw a missile trajectory, right? So at this moment here, it's traveling at 68.6 meters per second. At the top here, it's traveling at 0 meters per second. And at the bottom here, it's going to be traveling negative 68.6 meters per second. So it takes the same amount of time to go up as it does to come down. So the easiest way I think to do this is to figure out just basically how much time it takes for the missile to start at 68.6 and end at 0. So if we just do this as acceleration, which is, so we want our change in velocity to be negative 68.6 over time is equal to 9.8. So this should be about 7 seconds. So what I did here is I took the initial velocity, which is 68.6, and I figured out basically how much time it takes for the missile to basically stop at the very top. And to do this, I just took the acceleration is equal to change in velocity over time. I get that time is equal to 7 seconds. All right, to figure out the distance, what I'm going to use is, I'm actually going to use a different formula, one we haven't used so far. I'm going to use this one. X of t, or y of t, is equal to y naught plus 1/2 v plus v naught times t. So this right here is your average velocity. And this one is very useful for problems like this, where you need to figure out how far up or down something goes. So what I'm going to do is y of t is equal to, this is 0 because we initially start off at 0. And our average velocity is 1/2 times v, which is 68.6, plus v naught, v naught is 66.6. V is just 0 at the end, times t. So this is just going to be 34.3 times 7 y of t, which is, what is 34.3 times 7? This is like what, 238 or something? Something like this. Yeah, so this is how I would usually do this. I think there's the other way of doing it is where you use the general function. You set the position to be equal to 0, then you solve for t, then you divide t by 2, and then you do this, and then you plug t back. Yeah, so the other way of doing it is where you use your general function, I think. You would set your position to be 0. Basically, you're trying to figure out the total time it takes for your missile to start here and then end back at the ground. That'll give you the total time here. You divide that by 2 to figure out this time. And then you might plug this back into here to figure out how far up it went. That's another way of doing it. I think that way is a little bit slower and a little bit harder. But this way is harder conceptually, but easier mathematically. And then the other way is easier conceptually and harder mathematically. So those are sort of the ways I would do this. The next question, I believe, is just to see if they intersect. So what you're going to do is you're going to set this equation equal to the asteroid equation. What you're going to do is set this one equal to that one. So this one is, what is it, 60.6. So setting the missile's position function equal to the asteroid's position function, these will cancel like terms. So you'll get that 85.6 T is equal to 10,000. So you'll get that time is equal to, what is time equal to? Like, 116 seconds. And so since there is an intersection, that means the missile does hit the asteroid. If there isn't an intersection, then it doesn't hit the asteroid. And then for the velocity, position function, and displacement function. So for the acceleration, it's just going to be a constant negative 9.8. The velocity function, it's going to start off at 68.6. It's just going to keep going down. And then for your position function, it's going to look something like this, where you initially start here, circling down to this. So that's how you would do number 4. Does anyone have any questions about that?
Will there be like a recording of this on Canvas or like YouTube or something?
Sorry, say it one more time.
If we want to rewatch
So that's why I'm live streaming right now, because when it's live stream, it also gets recorded. So if you check the YouTube channel and the cameras announcement I posted out, you should be able to watch old recordings in there. So yes, you should be able to watch it again.
For B, are we allowed to just like put both equations into graphing calculator to find the height, or the one equation into a graphing calculator?
For 5B? For 4B?
4B, where it's 240 meters, because I got the same thing.
So, that's a good question. Yeah, that's fine, I think. That's fine.
Okay, thank you.
So we have 1 minute left in class. So I'm going to quickly wrap things up. So for homework, I want you to try to finish questions, 5 through 7. Do not do question 8. Do not do question 8. Question 8 was just if you finished everything really quickly and if you wanted a sneak peek of what we're doing on. Just do questions 5 through 7. And you don't need to turn it in. I just want you to do it just for quick practice. And what I will be doing is at the end of when you guys all leave, what I'm going to do is I'm going to just do it on the board. And so that way, when you want to see if you did it correctly, you can just watch the end of this live stream, and then you will be able to see how I do it on questions 5 through 7. So that way, you don't have to worry about, did I do it right or not? You'll see whether or not you did it right. And so so all these live streams and stuff are all posted on my YouTube channel, which I should have put in the Canvas link. So you should be able to see how I do it from there. Yeah. Does anyone have any final questions before I let you all go? Okay, otherwise you're free to go, and then I will see you all on Thursday. And I have office hours again, 2:40 to 3:40 as usual.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Mr. Hu, I have a question.
Yes, go ahead.
So for 4C, where the question asks if the missile will ever hit the asteroid, when you solve for it, you got like 117 seconds.
Yeah.
But the thing is, that value is like it's like they do intersect there, but it's not above 0. Like, so it's not really modeled. So it is the function, but it's not really modeled by the function. So would that still be a correct answer, even though they never intersect, like in the situation?
I didn't actually think about that. I never really double checked it. So it's so at t is equal to, oh yeah, you're right. So if it's negative 4.9 times t squared, this is what, like, if it's 100, it's like negative 49 times 10,000 or something. And then this is what, 68.6 times 100. So that's like 6860. Oh yeah, this is wrong. They never do intersect. Okay, that's like, no, I also I also didn't really check my math because I kind of forgot to, but you're right. They don't intersect. So that would not be an acceptable answer. The correct answer would be they never intersect.
Okay.
Yeah, I need to make that clear. Okay, thank you for bringing that up. Yeah, I had a feeling that when I wrote the problem, I'm pretty sure I wrote it with the intent that they don't intersect. But because they do have a meeting point, I was like sort of
Right.
like, okay, maybe I was wrong there. No, but you're correct. You're 100% correct.
Okay. Thank you,
Okay.
Mr. Hu.
Okay, is there anyone left here? Okay, so what I'm gonna do is I'm just gonna do question 5 right now on the board to my imaginary audience. So for question 5, I think it asks if the missile is moving at, what is how fast is it moving at? Moving at 4 meters a second up, and then it's okay. So let's first write position functions for both ones. I want to first write one for the asteroid. So the asteroid position is, it starts at 10,000 minus its initial velocity, which is 17, times time, minus 4.9 times t squared. So this is the position function of the asteroid. Then one for the missile. Position function of the missile starts at 0, so 0. I think it starts at 4. Does it start at 4 or 11? It starts at 4. The missile starts at 4 meters per second times time plus 11 times t squared. So this is the acceleration of the missile. So we need to determine, so the problem asks how much, so the problem is basically asking when do both of these hit 3 kilometers? So the first thing we want to do is we want to figure out, okay, when does the asteroid hit 3 kilometers? So to do this, what we're going to do is we're going to set 3,000 is equal to 10,000 minus 17 times t minus 4.9 t squared. So this 3,000 here is just for basically when does the asteroid hit this? So then it would be 0 is equal to 7,000 minus 17 times t minus 4.9 t squared. So let me just do this real quick. So this should be about 28.5 seconds. 28.5 seconds is how long the asteroid takes to reach this distance. So the next thing we're going to do the same thing, but for the missile. What we're going to do is the missile. We want to see how long does it take the missile to hit that same distance. So the 3,000 is equal to 4 times t plus 11 t squared. So I'm going to do it right here on my computer real quick. A is 11, B is 4, and C is negative 2,000. So just doing it on my computer real quick, you get that the time it takes for the missile to hit this location is t is equal to roughly 16 seconds, give or take. And so the missile, as you can see here, the missile takes less time to hit this location than the asteroid. So, which means that in order for them to intersect, both when the asteroid is at 3 kilometers, you're going to want to delay your launch by about 12 seconds. Yeah. That's for question 5. For question 6, so this is for question 5. For question 6, it's asking something kind of similar. Well, not really, actually. So the first thing we do is we're trying to figure out the initial velocity of the asteroid after it hits the ground in 60 seconds. So we're going to use the same position function here. But this time we want to figure out what our initial velocity is. So the final position is going to be 0. The initial position is 10,000 again. We don't know what the initial velocity is. So we're going to do plus v 0 times t, and then minus 4.9 t squared. Oh yeah, so t is 60 seconds, sorry. Okay, so let me do this real quick on my calculator. So hold on, I think did I do my math wrong? Come on, I need a BRB real quick. Use that. I'll be back. If you come back and like scroll forward to like 5 minutes in the video, and then I will be back to finish question 6. Okay, so it looks like I made a mistake. So it looks like I made a mistake. I changed the wording of the problem, so it shouldn't be 60 seconds anymore. So the problem with 60 seconds is that 60 seconds, you'll get that the initial velocity is positive, which shouldn't happen. So just ignore that. It should be, so I've already rewrote it, so it should start out at 40. That should be 40 squared. Sorry, this is just 60 is wrong. It's 40 seconds. Okay, so for this one, this is 70,840. Yeah, so what I just did here is I just filled in everything. I'm trying to figure out where it hits the ground. 10,000 is equal to V sub naught times 40, which is the time. This is 7,940, which is 4.9 times 40 squared. So again, my velocity is negative 54 meters per second. So the next thing we need to do is figure out how fast the Astrid and missile needs to be launched. So we're going to do something similar. Pretty much going to be the exact same thing, except this is going to be 20 squared. So this is going to be .9 times 20 squared. So 4.9 times 20 squared is that is this divided by 4, so that's 1960, I think. This is 10,000 plus 20 times V naught minus, I think this is 1960. Could be wrong. No, it's 1960. Yeah. So this should be. So this should be 80, 40 is equal to 20 times V naught. And so V naught needs to be negative 401 meters per second. No, 402. So the last one is for acceleration, I think. Missile with no initial velocity, but with an acceleration. So we're gonna do the same thing. 0 is 10,000. This is for part 3. I'm gonna ask for the rocket with no initial velocity. No initial velocity means that this is 0. So we're gonna do 1 minus 1/2 times A times T is going to be 20 squared. This is going to be $10,000 minus 200A. So this is going to be, A needs to be so this should be plus 1/2 squared. A needs to be 50 meters per second squared. So for question 7, what we're doing is we're looking at G-forces. So Saturn V has an acceleration of 3.9 Gs. Saturn V has an acceleration of 3.9 Gs. Now 1 G is just negative 9.8 meters per second squared. For this one, we're just going to use the absolute value of this. So 3.9 times this is I'm just going to say something around 39 meters per second squared. Something like this. So this is for the, what is the numerical value of the acceleration? For the Saturn V's actual acceleration. So if you think about it, the Saturn V is producing some amount of acceleration, and it's being pulled down by gravity, which is producing an acceleration of g. So in order to actually get the net acceleration of 3.9 Gs, Saturn V needs to go upwards of 4.9 Gs. Saturn V needs to go upwards of 4.9 Gs, and once you subtract gravity, you're going to get 3.9 Gs of force. So 4.9 Gs of force, and this is roughly 49 meters per second squared, something like that. Okay, so this next part is going to get really ugly really quickly. Really ugly really quickly. Okay, so what I'm going to do is I'm going to divide this into 3 sections. Now I'm going to start with section A. Section A, the rocket has an acceleration of, section 1, the rocket has an acceleration of how many Gs? 1.35 Gs. Okay. So the rocket is accelerating, so let's write a function for this. So the displacement function is going to be, so the rocket is first going to travel up 4 kilometers. So 4 kilometers is equal to the initial position of the rocket, which is 0, plus v sub naught 0, which is also 0. And so the acceleration is just 1.35 Gs. So 1/2 times 1.35 times t squared. This is your acceleration. And so you get that your time is roughly 77 seconds or so. So to figure out how fast your rocket's going, what we can use velocity with respect to time is your initial velocity plus 8 times t. Initial velocity is 0, so your velocity times time is 1.35 times 77, which is, what is it? $104. Okay, so section 2. The rocket, how fast is the rocket accelerating? It's at 7 G. So again, what we're going to do, so the final position of this is going to be 8,000. The initial position is 4,000. Final position is 8,000 because that's the second chunk. 4,000, this is because your initial position is 4,000 above the ground. So the tricky part here is recognizing that your initial velocity is no longer 0, it's actually this. So it's going to be 104 meters per second. 104 meters per second times t plus 1/2 times 7, which is 3.5 t squared. To solve this out, I'm just put it into my calculator real quick. A is 5, B is 104, C is 4,000. Oh, this is C, C is there, 4,000. So this should be 22 seconds. So to figure out the velocity after that much time, it's going to be my initial velocity is 104 plus my acceleration, which is 7 times 22. 7 times 22 is 110 plus 44, 154. So my final velocity at this point is 258 meters per second. For section 3, it's going to be 12,000 equal to 8,000 plus my initial velocity, which is 258 times t plus 4 times t squared. I'm going to solve this for t. It's going to be about 12.9 seconds. You not see that 12.9 seconds, give or take. And then let's figure out our velocity. It goes 258 plus 8 times 12.9. I'm just going to use 13 for this, just to make my life a little bit easier. 13 times 8 is 130, minus 26 is 104. So I'm just going to say it's about 104. So velocity is about 104 meters per second, give or take. Oh, no, this is 104. So 104 plus 158 is 362. 362 meters per second. That's my final velocity. Total time is equal to 22 plus 77. Oh, so this is a 22 plus 77 plus 13. This is 90 plus 2. So this is 112 seconds. So let's plot these. Let's plot up the velocity, position, and time. So my acceleration, let me start off with initial 1.35. Then it's going to be 7, and then it's going to be like 8. My velocity versus time, it's going to be like this. Essentially, my position versus time is going to be like you. Hopefully that makes sense. I had to calculate a lot of stuff as I was going through it, so it's not going to be perfect. This should hopefully be right. Yeah, and let me know if you have any questions. I would recommend pausing the stream here if you just want to look at the answers, because I'm going to close the stream in a couple minutes. So yeah, just pause the stream here.